Calorimetry for reaction of magnesium with hydrochloric acid. Calorimetry is a technique that we use to measure the heat energy that is exchanged during a chemical or a physical process. For this experiment, we will be looking at a chemical reaction that will occur inside a sealed test tube. The calorimeter that we are using is an insulated device, ideally prepared from 2 nestled styrofoam cups. So here we have 2 examples of how a calorimeter is set up. The example on the left has a thermometer and a stirrer involved, and this is the usual setup. When the chemical reaction or the physical change is occurring inside the calorimeter, something is added, the stirrer is used to homogenize the mixture, and the thermometer allows us to monitor the temperature changes associated with the transformations. The calorimeter on the right has a test tube that has a liquid level below the level of the water inside the calorimeter. It also has a thermometer connected to it, which will allow the monitoring of the temperature as a result of the heat absorbed or generated by the chemical reaction occurring inside the test tube. We're going to make the same assumption as before, that whatever heat is generated by the reaction or the process is the same as the heat that is absorbed or released by the water. And these two will have the same numerical value with opposite signs. So here is our experiment. We have a 0.0720 gram piece of magnesium ribbon, and we drop this inside 5.03 milliliters of a 3 molar hydrochloric acid solution. The test tube for the duration of the experiment is fully submerged in the coffee cup calorimeter, and the liquid level is consistently below the waterline. The coffee cup calorimeter originally contains 50 grams of water at 20.4 degrees Celsius, and after the reaction is complete, the temperature of the water will be 26.1 degrees Celsius. Our task here is to determine the heat generated by the reaction between the magnesium ribbon and the hydrochloric acid solution. We are going to make some assumptions. The first one is that there is no heat loss to the glass of the test tube. Whatever heat is exchanged between the reaction occurring in the test tube and the water inside the coffee cup calorimeter. The second assumption that we're going to make is that the solution of the test tube was constantly submerged, and even if there was some swirling around, the solution level did not rise above the waterline. Our first step is to calculate the heat of the water. For that, we're going to use the mass of the water, which is 50.00 grams. We're going to multiply that by the specific heat of water, which is 4.184 joules per gram Celsius. And then we'll multiply that by the temperature difference, which is final temperature, 26.1 degrees Celsius, minus initial temperature, 20.4 degrees Celsius. We close the parentheses and perform our calculation, giving us a heat of water of 1,192 joules. This should be a positive value because the temperature of the water went from lower to higher value. Once we have the heat of water, we are ready for the second step, which is to determine the heat of the reaction. If we were truly in an isolated system, then the heat of the reaction will be the opposite as the heat of the water, which means that the heat of our reaction is going to be the 1,192 joules of the heat of water with a negative sign. Because in order for the water to warm up, that heat had to come from somewhere, and it came from the reaction of the magnesium with the hydrochloric acid. Let's move on to step 3. Once we know how much heat was released in this reaction, we need to determine the limiting reactant in this reaction. For that, we're going to start both with the magnesium amount and the hydrochloric acid amount, and we will use both of those to determine the moles of hydrogen. We need a chemical reaction first to determine the mole ratios. Magnesium will react with 2 moles of hydrochloric acid to produce 1 mole of magnesium chloride and 1 mole of hydrogen gas. So starting with the 0.0720 gram piece of magnesium, we are going to convert our mass of magnesium to moles. 1 mole of magnesium is the same as 24.32 grams of magnesium. Once we have the moles of magnesium, we're going to convert to moles of hydrogen. So on the bottom, we'll place 1 mole of magnesium, and on the top, we'll place 1 mole of hydrogen. And from there, we simply calculate our value. It is 0.00296 moles of hydrogen. This means that if we were to completely consume all our magnesium ribbon, we would be able to produce this many moles of hydrogen. Now let's see how many moles of hydrogen we could produce if we consumed all our hydrochloric acid volume. We start with the 5.03 milliliters of solution. We convert from milliliters to liters by placing 1 milliliter on the bottom and 10 to the negative third liters on top. Then we convert from volume to moles using the molarity. On the bottom, we'll say 1 liter, and on the top, we'll add 3 moles of hydrochloric acid. From there, we use the mole ratio from the experiment. On the bottom, we'll say, in order to fully consume the 2 moles of hydrochloric acid, we would produce 1 mole of hydrogen. We end up with 0.00755 moles of hydrogen. The smaller of the 2 moles of hydrogen is the amount generated from the complete consumption of our magnesium, which means magnesium is our limiting reactant in the experiment. This knowledge is really important because in our next step, we need to find the moles of our limiting reactant. So we start with 0.0720 grams of magnesium, and we convert it to moles. On the bottom, we'll add 24.32 grams of magnesium, and on the top, we'll say 1 mole of magnesium. This is equal to 0.00296 moles of magnesium. If we know the heat that was generated by the reaction, and we know the moles of magnesium that were used to complete the reaction, then the next logical step is to divide the heat by the number of moles and determine the enthalpy of the reaction. So the enthalpy change of the reaction is the heat of the reaction divided by the number of moles of magnesium, which is our limiting reactant. Putting in the actual values, we have minus 1,192 joules divided by 0.00296 moles of magnesium. This will give us a very large negative value, minus 402,703 joules per mole. And considering the size of this number, it makes a lot more sense to convert it to kilojoules per mole. So the enthalpy change of the reaction is minus 403 kilojoules per mole. Now that we know what is the enthalpy change of the reaction according to the data we collected in our experiment, we can compare it to the enthalpy change of the reaction from the literature. And we can do it 2 ways. We can simply search for the standard enthalpy change of the reaction and use existing knowledge to perform the comparison, or we can use the standard enthalpies of formation and calculate the standard enthalpy of the reaction that way. We can look up the standard enthalpy of formation for the hydrochloric acid aqueous solution, and we can also look up the same value for the magnesium chloride in solution. So it is really important that we're looking for the AQ variety and not the solid for magnesium chloride and the gas for hydrochloric acid. The first task is to write a balanced chemical equation. We start with magnesium, which is in the solid state. It reacts with hydrochloric acid, which is aqueous, to produce magnesium chloride that is dissolved in water, so it is aqueous, plus hydrogen gas that we collected separately in a graduated cylinder. We need to balance the chemical equation, so we place a 2 in front of the hydrochloric acid, and we consider it balanced. In the next step, we're going to use the rules for determining the standard enthalpy change of the reaction, which is the sum of all the enthalpies of the products minus the sum of all the enthalpies of formation of the reactants. For this, we're going to say the standard enthalpy change of the reaction is, and first we start with the products. On the product side, we have magnesium chloride in the aqueous state. The standard enthalpy of formation of magnesium chloride in a water-based solution, plus the standard enthalpy of formation of hydrogen gas, from which we subtract 2 times the standard enthalpy of formation of the hydrochloric acid aqueous solution, plus 1 time the standard enthalpy of formation of the magnesium in the solid state. And with that, we close our parentheses. For the product side, we have the standard enthalpy of formation for the magnesium chloride solution, which is minus 800.1 kilojoules per mole, plus the standard enthalpy of formation of hydrogen is going to be 0 because the enthalpy of formation of elements as they appear under standard state condition is 0. So we can just add that 0 there. From these, we subtract the sum of the enthalpies of the reactants 2 times the standard enthalpy of formation of hydrochloric acid, which is minus 167.2 kilojoules per mole. Plus, this is all within the sum calculation, the standard enthalpy of formation of magnesium as it appears under standard state condition, meaning solid, which is 0. We close the parentheses dedicated to the reactants. From here, it is a straightforward calculation and find that the standard enthalpy change of the reaction is minus 465.9 kilojoules per mole. Comparing this value to the value we determined based on our experiment can give us a good idea of how effective our experiment was and how accurately we determined this value. If the numbers are very far off, we may want to repeat the experiment. If they are pretty close, but not exactly the same, we may consider the many ways in which experimental error could have kept us from obtaining the literature value.